All right, we're going to get into the meat and potatoes of descriptive statistics today. So we're going to start our using Excel a little more, looking at how to look at data. And I was going to start with the homework. Everybody see that okay?
Not yet. Yep.
So this is what I have so far. I think we have like just 4 people. I got to catch up. You know, it's like you don't want to get too far in. Everybody's cool here. And we'll go from there. So the homework last time was SIPOC. And I got Rob, right? Rob O'Connor.
Yo.
Hey, take us through this one. I love it.
Oh, was that
Oh,
mine?
no, it's Devin. He's not even here.
That's Devin.
Oh, actually, I was going to use yours. I ended up using Devin. So let me see if I got Dev on the.
No, I did purchasing a car.
Oh, yeah. Maybe I could have used that one too. Okay, let me. I think everybody's in that's in.
Devin's here today. It's just he's a little backed up on the floor right now. He might be a couple minutes late.
Okay, I'll go through with him. So again, this is great application of SIPOC. Determine the need for this is about universal. What's EOAT?
It's end of arm tooling, so it's like the robots.
Yep, the robots. So universal end of arm tooling robot custom setup. So do we need automation? Let's determine that first. Gather plate and parts, assemble, adjust the fit, pick part, mount to robot, create adjust robot program, start alongside injection molding machine, ensure process works, adjust, correct as needed. So you start with the P, then we go to outputs, process speed increased, process stabilized, operator repurposed, because you don't need an operator right at the end of it, maybe doing non-value added.
Sometimes we do, sometimes we don't.
Yeah, at least assist, like, so it's either a robot or a cobot.
Yeah.
And the customers are, I love that he did this, internal, my PTA, and also PTA's customer. And going backward, I'm gonna need to purchase some parts, requisition, fabrication, receiving parts, put away mounting plate, and then my suppliers, automation supply in the tool room. Nice. Excellent. So I'm Lane. Sal, you want to take us through that? I know that you did this at some point. I think you do all this, right? This is a really good swim lane process map.
Yeah, I did this for fall for that process for just kind of components moving through the tool room or being purchased. Starts in that top left corner, like if you need a component, there's kind of 2 ways we can go: you could make or purchase. If you purchase, it goes right to submit the RFQ to purchasing, and that's really it. Then you zip up to the item arrives. If you got to make it, there's a lot more steps. You got to get a copy of the print, order. We go through our machines we have in-house. That's ProtoTrack, CNC. Then they'll dip to the other swim lane is outside service. That's a heat treat. They come back for grind. And then there's kind of a decision spot, whether or not that needs additional processes after grind. It'll go either to Y or CNC again, or just be complete and added inventory.
I love it. You know, the thing I love about it, you know, again, the reason we do this, and a lot of times it'll work, it's really good at administrative processes, you know, so maybe John Maz is, and Ulbricht's done quite a bit of it. You know, but largely it shows you anytime I have a handoff, it's usually, you know, days, weeks, months, you know, sometimes every time I do that, there's going to be some waiting involved, right? And that's what it does. It's like an overall view. I'm not saying there's that much waiting in here, because I'm assuming there's 4 people that are involved that they have to get handed off to.
Yeah, departments for.
Yeah. And so the strategy is, all right, how do we eliminate or minimize the handoffs? That's the beauty of a swim lane map. And a lot of times it's because, you know, the people that are receiving the work aren't qualified or aren't trained to do the work. So they have to hand to somebody that knows. So excellent. Well, good, guys. I got a lot of good ones. I could have put a lot of them up there, but I just figured I'd pick 2. randomly. All right, you guys ready for some statistics?
Yep.
Oh, here, this is the meat and potatoes of this class. So basically the problem is, you're looking at my weight data from January 27, 2006. I weigh myself every day because one thing that, the NCAA will not tolerate is a dumb, fat official referee, right? So back in 2006, I'm not gonna say dumb, but I was fat. And I also, was having some issues, in terms of getting dizzy and just sluggish and all that. And so I decided I was going to weigh myself every day and I was going to record my weight on Friday every single week. So if you look at column B, you can see that there's 826 weeks of these weighings. All right. Now, the way I like to think about this and the reason why I'm using my weight is in terms of my health as a process. There's ways to measure the process, right? And weight is one of them. I'm going to be adding, I have data for blood pressure and pulse rate that you're going to see in the next bunch of weeks. But overall, we're talking about a process, right? So basically, I have about 826 pieces of data that you may collect. You probably do collect. You might have 15,000 pieces of data, right? You might be taking data points constantly. And, they're getting recorded. But the issue with data is it just lays on the page. It doesn't talk. It doesn't yell. It doesn't whisper. Nothing. If I take you guys through there, give you 5 minutes and tell me what's going on here, really difficult. So there's a bunch of statistics, descriptive statistics that kind of give us a feel for where we're at and make the data talk to us a little bit. All right. The first one is, what's the fattest, the heaviest I've ever been? I could go through and look at 826 lines and try to find it, right? Or I can go, this might be a review for some of you guys that use Excel all the time. And I apologize for that. For some of you guys that may not normally use Excel, it might be good, something new for you. But largely, anytime I want to start a function in Excel, I hit equals. And in this case, I think I'm going to type in max. And there's the first one that pops up, double click it. And then it's asking me for some data. So I'm just going to take the whole column and highlight it. And the fattest I've ever been since I've been measuring is 199 pounds. At 5'9", that's Michelin Man material. Minimum on the field on TV, even worse. The minimum, what do you think I do? Equals, start with an equals. Anybody
Min.
want to take a guess? Joey?
Min.
Thing. Right? It's pretty intuitive. Same thing, highlight. So basically the homework after today is going to be, I'm going to erase everything and you guys go ahead and do it. All right. That's going to be the homework. It's just getting practice going through the same data set. Now the range. So this is something I want to know, what's the difference between my max and my min? What's the range of numbers that I'm dealing with? So equals, and I'm going to highlight the max, sneak in a little minus sign, and then take the min. So I got 27 pounds between my Michelin Man and where I was a week ago, 172. I think that's the min. Now the mean is the same. Another word for that is the average. So again, equals average. Oh, learn how to spell. Click that. My average weight over the 826 weeks is about 184 pounds. Okay. Anybody idea what the mode is? Mode?
Number in the center of the data set.
All right. Or the one that happens the most often, okay? I think you're thinking of median, Brandon.
Yeah.
So let's do mode equals mode. Highlight it all. And this is the one that happens the most, 186. I think this morning I was 171. It's like, if you guys want a big round of applause. And then like Brandon just mentioned, the median. I like that. 184. All right, so you can see that my mean, the average, the mode, the one that happens the most often, and the median, the center point of my data, is all kind of close to the same, right? Next thing I want to know is what's the average deviation from my mean? So how many pounds is the variance on average of all this data from 184 pounds? So to do that, we're going to go equals standard deviation. When I type in ST, I get standard deviation P, which means population. Standard deviation S is sample. And 9 times out of 10, I'm going to pick S, right? 99 times out of 100, I'm going to pick sample because this again, I'm sampling my weight once a week, right? I'm taking a sample. So I hit that, and then it's going to ask me for the data again. So the average amount of pounds away from 184 is about 4 pounds. That's the average. Either way, 180, standard deviation is about 4 pounds. Okay. The standard deviation, one standard deviation is called 1 sigma. Okay. And then variance, which we're not going to use until we get into some formulas going forward. All it is a standard deviation squared times, squared. So it'll be 4.3 times 4.3. And the only reason it's significant at this point is because just so you're aware that we're going to use standard deviation sometimes in formulas, sometimes we're going to use variance. So equals vary. And again, I'm going to pick S for sample. And then I'm going to grab my data, hit enter. And 4.3 squared. So 4.3 times 4.3 is 18.6. That's my variance for this data set. So this kind of gives me a sense of, maybe it's not screaming at me, but it's talking at least, my data, right? And again, picture 10,000 pieces of data, not 200 and whatever this is, or whatever 600. Now the next thing I want to know is there's 2 things that I want to know about a data set, about my process. Right, one is the capable, but Six Sigma is about variation, right? And a graphical representation of a process that's in control, which would be my health, theoretically, is a normal curve, bell-shaped curve. All right, I'm going to explain that once after I make one. So in order to make one, first thing I need to do is I'm going to compare each data point to what we call a Z distribution. All right, and I'll show you, all you do is type 0 norm. It says normal distribution. And then it's asking me for a bunch of stuff. X, mean, standard deviation, and then it asks me a question at the end. So let me go through it. So first thing is X. So I'm going to grab that first piece of data, 194, comma. It's asking me for the mean, which I have right here, 184, comma. It's asking me for standard deviation, which is right here, comma. And then probability mass function for now, because we're going to get into it in a few weeks, just hit false. And then hit, before I hit enter, I have to take asterisks and put it on both sides of the mean and the standard deviation, on both sides of the letter. Because what we're going to do is we're going to drag this down all the way down to the last piece of data, but I want it to keep coming back to cell H2 and K2. Does everybody get that? That's all the asterisk does. It locks in grabbing the information from H2, which is the median, and K2, which is the standard deviation. So I'm going to pop in a couple asterisks on each side of those 2 letters. Hit enter. Hold on. I'm doing it again. when I do this, I just like, it's a lot easier than I'm making it. Equals X mean standard deviation false, and this is star. Doesn't look like I just did this. I don't think this ever happened. If anybody can help me, tell me if you see something.
I think to hold them down, you use dollar signs.
Aha! Ah, thank you, thank you, thank you. I don't know why I'm thinking excellent.
Glad I could help.
I know it's something stupid. I'm all rattled, as you can tell. Use the dollar. What do I use? Asterisks? Oh, my own. Don't get old, people. And then false. Watch how easy it is now. All right, good. Thank you so much. And I could actually click the corner. But I'm gonna just drag it down to, I'm actually sweating. Here we go. Now, graph it. Now I'm in a position I can graph it. And all I'm gonna grab is highlight date, hit the control button, hit weight, and Z distribution, insert, recommended chart. And there is my normal curve. It's a bell-shaped curve, as you can see. And obviously, you can label it whatever you want. Bill's weight. And you can see that it is a Z distribution would be where the mean, the mode, and the median is exactly the same. They'd all be 184 point whatever. In this case, they're all pretty close, 184, 186, and the median is 184. So it's a pretty nice bell-shaped curve. And a bell-shaped curve is significant because, again, the average, if I did have a Z distribution, then I can call this mean line, the peak, the tallest part of the bell, 0. And then I have 1, 2, 3, 4 standard deviations to the right and left, which would be 4 pounds in 4-pound increments, but it'd be 1, 2, 3, 4. I don't want to get ahead too far with that, but so this is going to be the homework, guys. And just remember, not asterisks, right? Right, Joanne? Dollar
Right,
signs.
dollar signs.
Yep, made it so much easier.
Show the money.
Go with the money. Is everybody good? Any questions there? Good? Good to go. God, I made that a lot harder than it should have been, right? Oh, stop share again. Oh my God, please hold. Oh my God. I went on vacation for too long. I'm off my game. All right. Wasting you guys' time. All right. Share. And quick review, it's been a couple weeks. All we covered, I think I have the review. Everybody see the slides okay?
Yep.
Yep. Right. it plays. Here we go. All right, so last time we got into process definition in the measure phase, so it's been a couple weeks. SciPoc, value stream mapping, basic statistics, data collection. Today one reason I love going to math practice first is because, as you'll see, the slides kind of confuse me more than they, believe it or not, even more than the math practice. So I like to do that first, and now the slides will just be a lot easier. So we're going to fly through these pretty much because we've seen most of it. And then next week, we're going to get into precision and accuracy, gauge R&R, bias, attribute MSA, and capability analysis. So here we go. So descriptive statistics describe what's going on. Countable data statistics. It includes organizing, summarizing, and presenting the data. And some of the tools are histograms, pie charts, box plots. And then inferential statistics, it's about making inferences about samples. And that's what we're going to be doing most of the time, right? We're going to see data sets. And a lot of times, like I could not get my weight population, right? I have to do a sample of it, whether it's 5 times a day or once a week or whatever. So I have to pull a sample that I'm measuring. In inferential statistics, they're analytical, and they include predicting and drawing conclusions, right? As you can see from just some of the simple things we did here. Or also, when we get into the analyze phase, when we start doing hypothesis tests, we're going to need to use those inferential statistics, because one of the things you may want to know is, hey, is Bill heavier during Christmas time, the month of December, or December and January, or does his blood pressure and weight go hand in hand, or the pulse rate? So the first step is descriptive statistics, kind of what we just did, and then we're going to get into some inferential, where we're going to try to make a sample talk about a population. And descriptive statistics, they summarize shape, location, and spread, right? But it doesn't provide inferences about a more general condition. So let's talk about location. Describes the value where the data tend to cluster around. Those are mean, the average, the median, which is the midpoint, and the mode, which is the one that happens most often. Those are all location, central tendency. And there's the mean. This is why I don't like to show, because they can see formulas like this, like, okay, I get it. It's like take every data, divide it by the number of them. That's my average. The median is the middle part of the data, as you saw. The mode is the one that happens the most often. Now, spread, measure of dispersion, range. So it's the difference between the largest and smallest value. The standard deviation, which is the average variance from the mean. So we saw in the case of my weight, it's about 4 pounds on average away from that mean for all that data, 820 pieces, weeks of measurements. And then variance is nothing more than the standard deviation squared. Joanne, you don't have to do the homework because you got me out of that jam with the $sign. The range is the numeric difference between the greatest and smallest values. You see how we can fly through now that we did it? The variance is how far on average the data spreads out. The deviation squared is the variance, the standard deviation squared. And there is the variance. And all we did was equals var sample. But there's the formula in case anybody's interested. And there's standard deviation, one for the sample and one for the population. And variance away from a target value increases the chance. And that's very important because, again, the objective is going to be, when you see a bell-shaped curve for any process, is to make it thinner, closer to the mean. And Six Sigma is all about variation and finding ways to eliminate Variation. Variation is the enemy of any quality process. So we have to understand, manage, and minimize process variation. So it all kind of comes together, right? You think about the variables with my weight, for example, it could be the holidays. It could be I'm going out for beer and sandwiches at football season. There's a whole bunch of X's that are going to determine that Y. And just as a reminder, here is our sigmas. Each of these, think of these sigmas as one would be 1 standard deviation, 2 standard deviations, 3. That's all sigma is, just standard deviation. And I think it's going to make a lot more sense to keep going. The distribution of normality, bell-shaped curve. A normal distribution is values are spread symmetrically around the mean. So some have a mean, and then some are larger, some are smaller, but it's symmetrical. I don't have a lot of outliers. A normal distribution can be completely described using its mean and its variance. Visually, the normal distribution creates a bell-shaped curve. So we did that by making a bell-shaped curve on my weight by using the mean and the standard deviation, if you remember. A z-distribution is the simplest one, and this is where the mean, the median, and the mode are all the same. And once I have a z-distribution, now on my graph, instead of saying 184 pounds where that 0 is, I could just say 0 there. And then in 4-pound increments, I go 1, 2, 3. So the 1 would be 1 standard deviation, which would be 4 pounds in the case of my weight, right? We figured that out. The z-score is the measure of how many standard deviations an observation is above or below the mean. And if a variable is normally distributed, they all have the same value. And the probability density curve of a normal distribution is symmetric. Nice, beautiful bell-shaped curve. If not, if I have a right skewed distribution, we're going to get into central limit theorem in a second, but the fix is go get more data. Because if I'm measuring a process, and I think my favorite process to think about is if I want to know the average weight of all killer whales, and I only pick 4 or 5 and weigh them, if I could, I may get one that weighs 800 pounds, one that's dying that might be 600 pounds, a baby one, who knows? But over time and continuing to sample, you're going to get the average weight of a killer whale. So a lot of times when I'm seeing right skewed distributions, when I'm not seeing a bell-shaped curve, it just means I don't have enough data. Go collect more. And the cool thing about once I get a bell-shaped curve, then I know that 68% of the data was going to fall within plus or minus 1%, plus or minus 1 standard deviation. Once I have a bell-shaped curve and my process is stable, now I know that 99.7% of my data is going to fall inside plus or minus 3 standard deviation. And this is significant. And I'll show you why. Because now here's my average right here, 0. And again, 68% are going to fall within 1 standard deviation. That means 34% are going to fall to the left. In case of my weight, it would be lighter. 34% are going to be heavier. And why is this important? Let's start asking questions like this. So let's pretend that the test scores of a physics class with 800 students. So there's 800 students that took the test. It's not like I gave the test to 9 people. So central limit theory is the more data I have, the more reliable it's going to be. They're distributed normally. So I got a bell-shaped curve. There's a lot of variation in it, as you can see, though. It's pretty wide bell shape. It has a mean of 75. So that was the average for the class, these 800 students, with a standard deviation of 7 points on the test. So my mean is 75. And then I could set up my curve where 75 plus 7 is 82, plus 7 is 89, plus 7 is, those are my standard deviations. And the same thing in the other direction. So now I could ask questions like, because I want to understand, was the test fair? Am I a good professor? Do I, or am I trying to blow people out of the water and make them fail, or, or am I too easy? So what percentage of the class has a test score between 68 and 82? Joanne, want to hit it? You're carrying me all day anyway.
No, you can handle it.
So what percentage of the class is between 68 and 82? Anybody? Be
34.
Yeah, 34 plus 34, right? Come between 68 and 82. So 68% of the class is going to be between 68 and 82. And if I take that 68%, multiply it times 800, I'm going to know exactly how many students scored between 68 and 82. How many students have a test score between 61 and 89? So again, same thing. I'm just going to add 13.6, 34, 34, 13.6, and that's going to give me, I take that total percentage, multiply it times 800, it's going to tell me the total number of students that have scores between 61 and 89. And then what's the probability that a student chosen at random has a test score between 54 and 75? The probability would be 2.14 plus 13.59 plus 34.134. That percentage would be the probability. All right. And how many students have a test score greater than or equal to 96? And you can see, because it's a beautiful bell-shaped curve, I know that this little piece of the curve here is 0.135. So I can just go 800 students times 0.135, and that's how many. That's the beauty of the symmetry of, once I get to a stable process where I don't have a lot of variation, I don't have a lot of outliers, I could do this kind of, make it talk a little bit. And why assess normality? There's many types of distributions, which we're going to get into. But a lot of processes have normal distributions, but not all business functions do. So, for example, if I wanted to measure the length of customer service calls into John and Joanne at Albright, you can't have a call shorter than 0, right? So I wouldn't really, I wouldn't have plus or minus there. So not all business functions will have a normal distribution. And it's also, if I know that my data is normally distributed, then it impacts how I can analyze it and interpret it. Like once I know that my weight, my blood pressure, and my pulse are stable, now I can start to do ask some questions of the process. Normality testing is going to be a homework in a couple of weeks, but basically if I have a huge set of data and I want to know if the data is normal, I can do a normality test, which if you do it longhand, it take you a week. If you do it with Excel, it take you like 5 minutes. So we're going to have that homework in a couple weeks. Central limit theory, as I mentioned, it's that as the sample size increases, data approaches a normal distribution. So if I'm building a new process, for example, and I'm collecting data and I'm getting data points all over, like the whale, if you think about it, if I collect more data, it's going to become a normal distribution. All right. Samples and sample means aggregate and shift until combined, they reflect the population's parameters. So we usually want to see a sample size threshold greater than 30. In the case of our test results, it was 800. And in the case of my weight, the same. A little bit more on graphical analysis. It's a method to visualize quantitative data. It's to discover the structure and patterns in data. And a complete statistical analysis, kind of like your dashboard, Marion guys, includes quantitative and graphical analysis. And a couple examples, graphical tools, box plot, histogram, scatter plot, run chart, and dot plot. Box chart plot is a graphical method to summarize a data set. So if we were going to do this with my weight, this is all about medians. All right. So I think I'm just going to go ahead and give you the example. So let's say I have I want to do a box plot. It's also called a whisker plot. I'll tell you why in a second. I think it says it on here somewhere. And it doesn't say it. It's also called a whisker plot. But basically, let's say I have this set of data here, 11, 22, 20, 14, 29, 8, 35. Well, I would sort them from smallest to largest. And then I draw a line like this down the bottom, 0 to 50. And the first thing I would do is find out, all right, what is the median? In this case, the median of all this data is 20. So that's going to be my Q2 here. And I'm going to take a line, a vertical line, and just put it at 20. Then I'm going to take the median from Q2 to my largest piece of data in 49. I'm going to take that median, and in this case, it's 28. So I'm going to draw another vertical line at 28 and do the same thing for the first quartile, it's called. Get the median between 20 and 8, and that's going to be 12, which is going to go right here. And then I just box it in. And then the whiskers are these lines. You can see from 8 here, like a plunger, to 49 on this side. And that's what those are the whiskers. And basically what it tells me is even though my data ranges from 8 to 49, a big chunk of my data is like if I did my weight over the last 4 years, say, this is kind of where it's going to land like this. For extra credit, if anybody wants to do a box plot on my weight, if you want, you got nothing better to do, right? You know, this is what it kind of would look like. You'll be skewed way toward the low end. And a histogram is it's another way to represent distribution of data. Adjacent rectangles over intervals with heights equal to the frequency density interval. And the total area is 100. A scatter plot. You guys have seen these. We're going to be doing some work with these a little bit. Present the relationship between two variables of a data set. A single observation is a data point. You can kind of see where the average is, the mean is here, the line, and how each data point falls on each side of the line. We're actually going to do this with when we do correlation between my blood pressure and weight, I believe, or pulse rate and weight. And the run chart, we're going to do a lot of these. When we get into the control phase, we're going to do control charts, but presents data in a time order, captures the process performance over time. And a dot plot, which I've never used in my life. It's an alternative to the histogram if you want to see the frequency of each individual value. Guess what? That's it. Everybody good? Ready to wake?
Yeah. Yes,
All right, so
sir.
I'm going to send you math practice. I'll send you the recording. Did I send you guys the slides already for the measure phase? If not, I'll get that. I'll include that on a PDF. They have them. Again, the homework will be just, I'm going to erase all what I did. Make sure you put dollar signs, not pound or asterisk, right, Joanne?
Yep.
I'm beating myself up for a couple of days. All right, have a great afternoon, guys.
Yeah, you too.
Take care.
Seeing y'all.
Hey, thanks, Bill.
Thanks, Bill.
See
You
you.
too.
All right.
Thanks, Bill.